All right, welcome to The Explainer. You know the drill. We take huge topics and we make them make sense. And today, we are going on one heck of a journey right inside the human body. So think about this. You've got a killer headache, you pop a pill, and like 30 minutes later, poof, it's gone. But have you ever stopped to wonder what actually happened in those 30 minutes? Where did that little pill go? Yeah, it's definitely not magic, even though it can feel like it. It's actually a super carefully choreographed journey. You could say it's a story with four main parts. And the science behind that story? It's called pharmacokinetics. Okay, so let's kick off this epic journey. To really get it, though, we first have to clear up the difference between two really important and often confused ideas. You can think of it like this. There are two sides to every coin, right? Well, with medicine, there's pharmacodynamics. That's what the drug does to your body. You know, it eases the pain, lowers your blood pressure, that kind of thing. But today, we're flipping the coin over. We're talking about pharmacokinetics, what your body does to the drug. It's like we're tracking the drug's personal travel itinerary, from the moment it enters till the moment it leaves. And this travel plan, it's got four main stops. And lucky for us, scientists gave us a super handy acronym to remember them. ADME. That stands for absorption, distribution, metabolism, and excretion. So ADME, that's going to be our roadmap for the rest of this explainer. Simple enough, right? All right, let's dive into stage one. Before a drug can do anything, it has to get in. This is absorption. So here's how to think about it. When you swallow a pill, it's got to make its way from your stomach or your gut into your bloodstream. That whole process is absorption. But what if you get an IV? Well, that's like getting a VIP all-access backstage pass. The drug gets dumped directly into your blood. No waiting, no lines. Absorption is instant, and it's 100%. So how in the world do scientists actually track this journey? Well, it's pretty cool. They can take little blood samples over a period of time and measure exactly how much drug is floating around in there. And when you plot that data, you get a graph. It's like a visual diary of the drug's life inside your body. And this graph gives us some really important clues. The first one is called Cmax. If our drug's journey is like climbing a mountain, Cmax is the absolute peak. It's the summit. It's that single point in time when the concentration of the drug in your blood is at its highest. Okay, the other big one is called the area under the curve, or AUC. Now, don't let the name freak you out. You don't need to do any calculus here. Just think of AUC as the total amount of the drug your body gets to see over its entire trip. It's the whole shebang from start to finish. Okay, so the drug made it into the bloodstream. Great. But the journey is far from over. Now it has to actually get to where it's needed. This brings us to stage two, distribution. Distribution is all about how the drug gets from the blood, which is kind of like the body's superhighway system, out to all the different neighborhoods, you know, the tissues and organs. Now, it's got to find its target address to do its job. But here's the thing. It also takes a bunch of detours to other places, and that is often what causes side effects. So where does it head first? Well, it all comes down to traffic, or in this case, blood flow. Scientists call this perfusion. Organs that are like major city centers with tons of blood flow, like your kidneys, they get flooded with the drug almost immediately. But then you have places with, let's say, less traffic, like body fat. The drug gets there, but it takes a much, much slower, scenic route. But hold on, here's a really critical plot twist. For a drug to actually do anything, to leave the highway and get to its destination, it has to be, and this is the key word, unbound. It has to be free. See, in your blood, a lot of drug molecules love to grab onto these big proteins, kind of like a remora on a shark. When a drug is bound like this, it's basically stuck. It's too big to get off the highway, it's just along for the ride. Only the unbound or free drug molecules are small and nimble enough to actually exit the bloodstream and go to work in your tissues. All right, so the drug got in, it traveled around, it did its thing, mission accomplished. Now it's time for the grand finale, getting it out of your system. This final act starts with metabolism. And for this, you gotta think of your liver as the body's master recycling and processing center. Its main job is to take that drug and chemically tweak it, usually to make it more water-soluble. Why? Because that makes it way easier for your body to flush out. And here's a wild card. Sometimes the byproducts of this process, these things called metabolites, can actually be active themselves. Sometimes they're helpful and sometimes not so much. And that chemical change sets up the very last step, excretion. This is the final goodbye. It's the irreversible removal of the drug and its metabolites from your body. And there are a few main exit doors. The kidneys are the big one, flushing it out in urine. The liver can also get rid of it through bile. And hey, you're even getting rid of some things just by breathing out. So there you have it. Absorption, distribution, metabolism, excretion. ADME. The complete journey. But, so what? Why should you care about any of this? Well, you should care because a drug's ADME profile has everything to do with your experience with medicine. It's what determines your dose, how much you take and how many times a day. It explains those annoying side effects. That's just the drug getting distributed to a place it wasn't supposed to go. And this is a huge one. It explains drug interactions. A lot of those happen when two different drugs are basically fighting for the same machinery in your liver during that metabolism phase. Yeah, let's focus on that elimination part for a second because it's really, really important. The speed at which your body gets rid of a drug can work in two different ways. It can be constant or it can change. Let me show you exactly what I mean with a quick example. Okay, so what we're looking at here is half-life. That's just a fancy term for the time it takes your body to get rid of half of the drug. Now check out drug A. Whether you take a low dose or a high dose, the half-life is always the same, 6 hours, rock solid. But now look over at drug B. Whoa. As the dose gets higher, the half-life gets longer and longer. You see that pattern? So which one would you rather take? Drug A, right? It's way more predictable. That constant half-life tells us it follows something called first-order elimination. Most drugs work this way, and it makes them much safer and easier for doctors to prescribe. Drug B, on the other hand, it's unpredictable. Its elimination system is getting totally overwhelmed as the dose goes up. That's a classic sign of what's called zero-order kinetics, and it can be a lot trickier to manage. All right, let me leave you with one last thought that really ties all of this together and shows you why this stuff is so critical. Remember how we talked about drugs being bound to proteins? Well, some drugs are 99% bound. Think about that. That means only 1% of the drug in your body is actually free and active. Just 1%. Now, what happens if you take another drug that competes for those proteins and just bumps 1% of the first drug off? You might think, oh, it's just a 1% change. But no. You've gone from having 1% of the drug free to having 2% of the drug free. You have literally just doubled the amount of active, powerful drug floating around in your system. And that right there is why drug interactions can be so incredibly serious. Understanding this journey isn't just cool science, it's knowledge that can genuinely save lives.